Okay, so hello and welcome everyone to the 12th week of interactive live sessions for the course on fundamentals of convective heat transfer. This course is being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras, and like every other week, we shall be solving some problems together. Now, this is corresponding to the uh, lectures of the last week of this course, which focused on boiling, condensation, and phase change of materials. And so this is technically the last session we'll be having, but we will have another one, another revision session tomorrow from the same time, 6 to 8. All right. So without any further ado, let's move into the thick of it. So we have question number one, which is asking us in the pool boiling curve, the point after the onset of nucleate boiling, where the heat transfer rate is minimum, is known as what? Option A, the inflection point. Option B, the Leidenfrost point. Option C, the critical point. Or is it option D, none of the above? So if we quickly try to recall what the sorry what the pool boiling curve looked like. So we had excess temperature T, delta T on the x-axis, and the heat transfer rate Q dot double prime on the y-axis, and we looked at how how the heat transfer rate varied as a function of this excess temperature delta T. So we saw initially it started off small, then we had a start of nucleate boiling where it went up, it reached a maxima, then came down, reached a minima, and then started increasing again. So uh, some point around this is the onset of nucleate boiling, also written as ONB. Actually, it comes a bit earlier, but okay. And this reaches a maximum point. There is one important point here, and here is the minimum point that we are interested in this question. So in the pool boiling curve, the point after the onset of boiling, where the heat transfer rate is minimum, is what? So this onset of nucleate boiling is only to say that everything you have to consider the minimum in the right side of this curve and not in the left side because for a very small delta t, the Q will anyway be minimum. So the global minimum lies somewhere here, but that's not what we're interested about. We're interested in the minima after the onset of nucleate boiling. So which specifically refers to this point, this minima here. So what is it known as? Is it option A, the inflection point? Is it option B, the Leidenfrost point? Is it option C, the critical point? Or is it option D, none of the above? So let's take a look at the answer. It's actually the Leidenfrost point. So I'll go back to my curve over here and discuss the other point. So this is known as the Leidenfrost point. Uh, this is the critical point. This here is the critical point. This point where the curvature of the curve changes, meaning that the slope before this point was increasing and after this point starts decreasing. The slope is anyway positive. It's the rate of change of slope which changes over here. And not only changes, it becomes zero over there. So it was positive earlier, becomes zero at that point, and becomes negative after this point. And this is known as the inflection point. And this minima over here, this is the Leidenfrost point. So I'll remove this question mark. Sorry. This is the Leidenfrost point. So phenomenologically, what happens here is that uh, if we are looking at pool boiling here, so this is the surface which is heated, and we will see. So in the onset of boiling itself, we have some bubbles forming in the surface and going up. In the critical point, it becomes, or after the nucleate boiling, if we keep on increasing the excess temperature, these nucleation points will grow, they will coalesce, and it will form bubble columns in the vertical direction, as well as bubble films will form in the surface. and they will become blankets and start covering the region of contact between the solid where it's being heated and the liquid. And what happens in the Leidenfrost point is that the entire surface, so this entire surface gets covered by a vapor film over here. And that prevents heat transfer, which is why the rate of heat transfer is minimized at this point. Now, beyond that, if we keep on increasing delta T, radiation will now start to take over, and convection and conduction will start playing lesser roles, and that leads to the increase in heat transfer beyond the Leidenfrost point. But it's the vapor film entirely covering the contact region between the fluid and the solid, which leads to the minimization of heat transfer, and that particular delta T is known as the Leidenfrost point. All right, so hope that's clear. Moving on to question number two. We have now different stages of flow boiling. So we saw pool boiling earlier, and now it's flow boiling. And in flow boiling, you have, six different stages given here in the question. You have to arrange them in the subsequent order of increasing delta T, of increasing delta T. So what I mean here is that I have, let's say, a huge copper tube like this, a solid tube which is heated, and I'm flowing some liquid through here. So some liquid is flowing in through here, and it's getting heated by this tube. Now, that will lead to different stages of multi-phase flow eventually. Now you have the different stages of flows are characterized by these different names, namely option A slug flow, option B mist flow, option C annular flow, option B bubbly flow, option E single phase liquid flow, or option C single phase vapor flow. You have to arrange them in order of increasing delta T, or rather, if I'm heating the fluid and making it and forcing it to flow this way, then increasing delta T will also be this way, going upwards. So which stages of flow will you encounter first and which stages of flow you will encounter later? You have to arrange them in that order. So let's take a look at the solution. We have a solution here, but let's try to figure it out ourselves. So once again, I'll draw the figure a bit bigger this time. I have single phase liquid coming in through the bottom. So initially I will have entirely liquid here. So this is single phase liquid flow, which is option E. So this is E. Then, just like in nucleate boiling, little bubbles will start forming, and they will flow along with the liquid. So I'll have majorly liquid in this entire region with small vapor bubbles here and there, interspersed within the continuous medium, which is still majorly liquid. So this regime is known as bubbly flow because there is a liquid flow with bubbles entrapped within it. So that's option D, bubbly flow. Sorry, that's bubbly flow for you. Then after that, these bubbles will keep on growing bigger and coalescing with each other, forming these bigger slugs like this. There will still be small bubbles, but big slugs will start forming and covering more volume of the entire fluid. And these coalesced pockets of vapor, these are known as slugs. And this kind of a flow is known as a slug flow, which corresponds to option A. This is known as slug flow. And after this, these big slugs, they will also keep on coalescing with each other and growing bigger, and they will cover the entire, the inner region of the fluid, inner region of the duct. So we will get this very clear vapor in between, and liquid will stick to the edges of the tube. So And this kind of a flow, this is known as annular flow because the vapor uh, covers up the entire annulus of the uh, duct, or rather, the vapor occupies the inner section of the duct, and the liquid is present in the annulus of the duct, which gives it the name annular flow, which is option C. So after A, we get C. And if we keep on heating, this entire liquid film will also evaporate out, most of it, and we will get the continuous phase or the major phase of this region will become entirely covered by vapor, but it will still have small droplets of liquid still contained within it, which has not evaporated. So that's known as a mist flow. So this is like a mist which comes out of a, let's say, a perfume bottle. If you spray, it forms a mist of small liquid droplets suspended in air. So that's like a mist, uh, which is option B, that is mist flow. And after this, these liquid droplets, they also evaporate out and it becomes entirely vapor. And that is known as the single phase vapor flow. So there's no more liquid remaining in this. And that is our option F. So going from bottom to top, we get E, D, A, C, B, F. And that should be the correct order. E, D, A, C, B, F. This is the solution. All right, so let's take a look at a similar problem once again. We looked at flow boiling and stages within it. Now we will look at pool boiling and the stages within it, and in the similar increasing excess temperature. So in this case, we don't have a flow. We have, the liquid contained in a pool like this, a closed container, which is not moving around anywhere. But there is a temperature difference between this solid surface and the liquid, and that temperature difference is this delta T. And that will dictate the stages of or the state of the flow or the fluid in between. And there are different forms of boiling, namely option A, film boiling, option B, natural convection boiling, option C, nucleate boiling with bubbles reaching the surface, and nucleate boiling with bubbles collapsing. So these are two stages of nucleate boiling. And we have option E, transitional boiling. So once again, you have to arrange them in order of increasing excess temperature. All right, so let's take a look at the solution. We have a solution here, but we will like to verify it. So it initially, when the delta T is small. So here for reference, we will keep an eye out on the pool boiling curve, which we also saw earlier. So we had something of this sort, right? Yeah. So initially when delta T is low over here, we have, there are no bubbles. There's just, a hot surface trying to heat the whole pool of liquid, and, the fluid near the bottom surface, it will get heated first and try to rise up. Sorry. It will rise up, and colder fluid from the top will try to come down, setting up this natural convection currents, which we saw earlier. And this is natural convection boiling. So this is, uh, where is it? This is option B. Then we will move into, bubbles forming. So we saw onset of bubble boiling over here, right? O and B. So now bubbles will form, but since the rest of the liquid is lower at a temperature lower than the saturation temperature, these bubbles will collapse as well. By collapse, what I mean is that a vapor bubble forms at the bottom of the pool, and as it goes up, it loses heat to the cooler fluid surrounding it, which lies on top. And as a result of losing that heat, it will, once again condense back into liquid. So bubbles will uh, start shrinking, and they won't be ultimately able to reach the surface. They will collapse before reaching the top surface. So this is the first stage of nucleate boiling with bubbles collapsing. So that is stage D, nucleate boiling with bubbles collapsing. Now, After this stage, what happens is that, we get bigger bubbles and a get greater frequency of these bubbles forming. So they don't entirely collapse, they do become smaller, but in the end, they reach the surface and burst open over there. So this stage is known as nucleate boiling with bubbles reaching the surface. That is stage C, right? Now, moving far beyond it, we saw earlier that these bubbles will now start coalescing with each other. So let me draw the different things that happens. One thing is if the frequency of these bubbles releasing increases, then they coalesce vertically. So if I have, multiple bubbles like this in the vertical region and they coalesce with each other, I will form a continuous jet like this. So this is one thing that happens, and multiple bubbles growing nearby, they will also coalesce with each other, leading to a bigger blanket like this. So these are the different things that will happen, and this region is known as the transitional region, which is stage E. It is transiting from a nucleate boiling towards film boiling, which is the next stage. And so moving even further from here, we saw these film blankets forming in the surface. If they keep growing and many other film blankets form, they will now connect with each other and they will cover up this whole contact region between the solid and the liquid. So as a result, we will get a film of vapor in between. And this stage is known as film boiling. And this is where the Leidenfrost effect happens, as we saw earlier. So it's over here. Here, the rate of heat transfer also reaches a minima since it's onset of nucleate boiling. So these are the stages B, D, C, E, A, which is the correct order uh, arranged in order of increasing excess temperature. Right. So this phenomenology is very important, and you have to keep that in mind. All right. So moving on, we'll move on to question number 4, which is testing your knowledge of what the heat transfer coefficients typically are for condensation. So the convective coefficients, which we also known as H, for condensation usually lies in the range what? Is it option A 30 to 300 watt per meter square Kelvin, option B 50 to 2000, option C 200 to 10,000, or is it option D 5,000 to 100,000 or 1 lakh? So you have to remember condensation is a phase change process where latent heat is involved. And so what's the typical convective heat transfer coefficient for phase change? So you must have guessed it correctly. It's option D. It's very huge. It's above 5,000 to 10 lakh or even more in extreme cases. All right. So it usually goes this way that natural convection is the smallest, then uh, forced convection is a bit higher than that, and phase change is the highest. So this is the order in which H goes. So H keeps on increasing as we go from natural to forced to phase change, heat convection. And since condensation is is a phase change process, it has a huge convective heat transfer coefficient. Okay, so let's move on. We have question number 5 asking us, dropwise condensation usually occurs when or where rather? Do they happen in option A, oily surface, option B, glazed surface, option C, smooth surface, or option D, coated surface? So what I mean by dropwise condensation is that, let's say if I had a solid surface like this, which is cooler than the vapor on the other side, then that vapor will now lose heat and change its phase into liquid and form small droplets, individual droplets on the surface of the solid. In contrast, there is another thing known as film condensation, where instead of forming individual droplets, it forms a continuous thin film of liquid after condensation. So let's take a look at the solution. It's option D, coated surface, which facilitates dropwise condensation. So if you coat a certain solid with some other material, usually, an example of it could be Teflon coating on some stainless steel solid surface. These kinds of coatings usually, facilitate dropwise condensation. Basically, the physics is that if you have, uh, you know, uh, if you can create a high enough or the optimal surface tension between that vapor and the liquid form of that particular vapor, then you can form droplets which will hold itself instead of coalescing into bigger ones. Okay. Cool. So moving on, we have, from the Nusselt analysis of laminar film condensation, which was covered in hopefully the second lecture of this series of this week, where we saw how to derive the film thickness delta as a function of x, where let's say we assume that the film thickness delta varies as x power n. Now that index n is equal to what? Is it option A 1 by 4, option B minus 1 by 4, option C 1 by 3, or is it option D 3 by 4? So what we did here is that we had a vertical film like this, or a vertical surface like this, which was being which was cooler than the vapor on the other end, and it did not lead to drop condensation, but rather it led to film condensation, and that film started flowing downward along with more condensation happening. So we had sort of a boundary layer forming like this. Let me draw a more smoother curve, something like this. So let's say if this was x and this thickness was delta, the delta varied as a function of x, and so x varies as a function of x. You needed to find this n, this index n, like with what rate did it grow? All right, so if you go back and take a look at the derivation, uh, we found that delta actually varies as x powers 1 by 4. So what this means is that if you increased x 16 times, so let's say going from x equal to 1 to x equal to 16, we will see delta doubling over that period, right? So what I mean is this, that so once again, if I had something like this, I had, let's say, x equal to 1. If I went to x equal to 16, and I had, let's say, delta 1 here and delta 2 here, then delta 2 would only be twice of delta 1 after moving 16 times in the, increasing the x coordinate by 16 times. So it grows, but very slowly. All right, so we'll move along to question number 7. This is a very simple one, asking us that the nucleate boiling phase is not influenced by surface characteristics of the solid in contact with the liquid. Now, is this statement true or is it false? Let's take a look at the solution. It's actually false because it is indeed influenced by surface characteristics. So this statement is false. So the surface characteristics actually dictate a lot of where these bubbles will nucleate and start to grow. So let's say if you have a very rough surface, that might increase the rate of heat transfer, right? And influencing the whole fluid mechanics of the problem as well. All right, so moving on to question number 8 now, which is hopefully the last question of today's session. It's asking us that for Reynolds number in this given range between 30 to 1800, the flow regime in film condensation over a vertical plate is what? Is it option A, wave-free flow, option B, turbulent flow, option C, wavy laminar flow, or is it option D, stratified flow? So once again, we are looking at film condensation over a vertical plate like this. So given that the Reynolds number, and I should mention here that let's say this is, if this is X, then this Reynolds number is with respect to X. In this regime, what happens to the flow? Is it wave-free flow? Is it turbulent flow? Is it wavy laminar flow? Or is it stratified flow? Let's take a look at the solution. It's wavy laminar flow. So as it turns out, so it starts out, so Reynolds number increases along with X, right? So initially we have, wave free laminar flow where, the streamlines, if I draw, they are lines which do not cross each other and they are pretty smooth lines. Now, after this, some instabilities start growing and we can see waves in this streamlines. And that is wavy, but still it's laminar flow because it hasn't shifted to turbulent yet. But after this, a transition goes on, and after this, we will have, you know, initially a transition and then finally a turbulent flow. So that makes sense, right? As the Reynolds number increases, the instabilities have a higher chance of sustaining and making the flow turbulent. All right, so hope this was helpful. That's all. Thank you. We will meet again tomorrow.